Hello students, welcome to my lecture series on reinforced concrete structures. In this class, I am going to discuss about design of doubly reinforced beams as per limit state method IS 456-2000. So outcomes of today's class are, after completion of this class, we are able to know what are the design steps for designing a doubly reinforced rectangular beams. Let us recall what are the things we have discussed in our previous classes. That is, I have discussed in previous class the analysis of doubly reinforced beams. So what we did there, we have designed what are the steps for calculating moment of resistance. Based on the steps, we have solved some numerical problems and calculated moment of resistance. Let us recall those steps again. First of all, what we did, first we have to calculate FSC. What is FSC? FSC is the stress in steel in compression zone. That can be calculated based on D dash by D ratio, that is ratio between effective depth in effective cover in compression to the effective depth of the beam and the given grade of steel. So based on these two values, we can calculate what is the FSC is as per table F of SP16, that is special publication 16. Based on those table, we can calculate what is the FSC is. After calculating FSC, we have to calculate what is the actual depth of neutral axis. So you know how to calculate actual depth of neutral axis, whether it is a singly reinforced beam or doubly reinforced beam. The procedure is same for calculating actual depth of neutral axis. This can be calculating by equating total compressive forces is equal to total tensile forces. By equate that, you will get a formula for XU. From that XU is nothing but actual depth of neutral axis. If you substitute the values related to FYA, FCK and all, you will get what is XU is. After calculating XU, that is actual depth of neutral axis, calculate XU max or XU limit, I can say, that is limiting depth of neutral axis. So this can be calculated based on a given grade of steel. As per given grade of steel, we have a ready-made formulas. Say for if you take Fe415, we have a 0.5 times D, that is equal to XU max. Here D is the effective depth of the beam. From that we can calculate what is the XU max is. After calculating XU and XU max, we have to compare these two values for deciding type of section. Say if you know that Fu is equal to XU max, XU equal to XU max, then I can call it as a balanced section. If XU is less than XU max, it is over reinforced section, under reinforced section. If XU is greater than XU max, it is a over reinforced section. So based on that, we can calculate what is the moment of resistance is. So those things we have discussed in our previous class. Now we will start design part of a doubly reinforced beam. So, you know, any design of any member or any beam, ultimately what you have to find out? You have to find out cross-sectional dimensions and area of steel required in that particular section of a beam. But in the case with the doubly reinforced beam is, as you know, when we adapter, in what situation we will go for doubly reinforced beam is. The one major situation is when there is a restriction for increasing the dimension. So basically doubly reinforced will be provided when our applied moment bending moment is greater than limiting moment of resistance. To enhance this limiting moment of resistance, we have to increase the dimension of the beam. So especially we will increase the depth. But there we have a constraint. So here your dimension are fixed. For fixed dimension, you have to calculate what are the area of reinforcement, right? As like your design of singly reinforcement beam, there we have calculated AST, B and D. But whereas in doubly reinforced beam, here B and D are fixed because of some restrictions, and we have to calculate what are the area of reinforcement, that is in compression zone and tension zone. Say we have a beam here. Say this is a doubly reinforced beam, as we are provided reinforcement in the tension zone as well as a compression zone. The design of this type of beam means this B and this D are fixed for given beam, and load are given to you, and grade of concrete, grade of steel will given to you. Based on that, you have to calculate what is the area of this reinforcement and what is the area of this reinforcement. What is this reinforcement? That is a tensile reinforcement. So we have to calculate AST. What is area of tension reinforcement? And this is a compression reinforcement. Here we have to calculate what is the ASC is, area of compression reinforcement. If we calculate these two, then it is design is over. After calculating those values, we go for checks, say some flexural checks and shear checks. So in flexural check, we have a minimum area of reinforcement provided and maximum area of reinforcement provided. As per Codal provision, we have to check those values, and then we go for a deflection check by calculating basic value into a modification factor. Same thing what we did in our singly reinforced beam, same thing we'll do here. And what are the things we have steps followed for design of shear reinforcement for a singly reinforced beam. Same step will be followed for this also. So let us see to design completely a rectangular doubly reinforced beams, what are the steps to be followed? Those steps we will discuss one by one now. So let us start with the first step. First we have to calculate determination of AST, that is area of tension reinforcement. You know, AST is here area of a tension reinforcement of a doubly reinforced beam, and ASC is the area of a compression reinforcement. As per our analysis purpose, we have divided this beam into two simple sections, say section 1 and section 2. Section 1 is related to we are assuming it as a balanced singly reinforced beam. What is that? It is a balanced single reinforced beam. You know what is a balanced beam means, right? And it is some imaginary beam. We are assuming as a section 2. Say it is the area of steel corresponding to the balanced section is AST1, and area of tension steel corresponding to this section 2, this is called additional reinforcement. The area of additional reinforcement is AST2, and we know what is the bending moment coming onto this beam, and what is the limiting bending, what is the maximum bending moment of balanced section, and to counteract this amount of bending moment which is coming on that, how much additional moment we require to counteract this the moment which is coming due to the externally applied load, that is additional moment mu2. This additional moment will be generated from what? This moment will be restricted by the area of reinforcement provided in compression zone. So this value we know, this value we can calculate. From that we can calculate what is mu2 is, that is a moment of resistance in section 2, that is mu minus mu limit. So let's see, this is the stress distribution diagram. Now we have to calculate area of steel corresponding to singly reinforced balanced section. So this is the stress block corresponding to the doubly reinforced beam. Now we have to calculate with respect to section 1. Section 1 means this. With respect to balanced section, we have to calculate what the area of steel AST1 is. So AST1 can be calculated, that is mu limit equal to 0.87 Fy AST1 into d minus 0.xu max. So how we obtain this? You know that moment of resistance we can calculate with respect to compression or with respect to tension, right? If you take the compression, you will not get directly what is AST value in that formula. If you take that with respect to tension, we will get AST value. Say in the moment of resistance, it is a tension force, and this is the lever arm for the compressive force. You know that this force multiplied by perpendicular distance, that lever arm, will give me the moment of resistance of a balanced section or any section, say for with respect to tension. As we are calculating is area of steel corresponding to singly reinforced balanced section, we know that the depth of neutral axis XU will become XU max for balanced section. So in place of XU, we have to substitute what is the XU max is. Finally, the moment of resistance corresponding to the balanced section is mu limit, that is ultimate moment of resistance, or I can say it is a maximum moment of resistance. So that is, I am calculating with respect to steel, that is 0.87 Fy AST1 for the balanced section, for section 1, that is lever arm is d minus 0.42 XU max. From this, if we rearrange the terms, we will get AST1 equal to mu limit by 0.87 Fy into d minus 0.42 XU max. So this is how we can calculate our AST1. Remember this is AST1 is the area of a tension steel corresponding to the balanced or singly reinforced section, right? Next we have to calculate area of a tension steel corresponding to section 2. So this is corresponding to section 2. This is the section 2. This AST2 we have to calculate. For calculating this also, we have to take our moment of resistance corresponding to the tension reinforcement only. So here, if what is the perpendicular distance for this? See, this is a 0.87 Fy AST2. Say the force in tensile reinforcement corresponding to the section 2, that is 0.87 Fy AST2. And what is the perpendicular distance between these two? this will be given the lever arm, that is effective depth minus effective cover in compression zone, that is D minus D dash. So finally moment of resistance, that is mu2 corresponding to section 2 is 0.87 Fy AST2 into D minus D dash, right? So if I rearrange the term again, you will get AST equal to mu2, that is the moment of resistance corresponding to section 2 by 0.87 Fy into D minus D dash. So now we have obtained from section 1 the area of tension steel is AST1, from section 2 is AST2. If you want to know what is the total tensile reinforcement in doubly reinforced beam, that by adding AST1 and AST2 we will get that. So finally AST equal to AST1 plus AST2. So this is how we calculate what is the area of tension steel in doubly reinforced section. Similarly we have to calculate what is the area of compression steel. Again, the compression steel corresponding to the section 2, in section 1 it is only a balanced section of singly reinforced beam. So in the balanced section of singly reinforced beam, we have to provide reinforcement in tension. Now in section 2, we have provided reinforcement in compression as well as tension. The compression we have provided because of to develop the additional moment of resistance, to counteract that additional compression force reinforcement forces. Then we have provided some reinforcement, that is additional reinforcement in the tension zone of a section 2. Now based on that we have to calculate what is the area of compression steel corresponding to the section 2, that is mu2 is equal, if you go here, say this one, mu2 is the moment of resistance in this section, that is equal to the force in FFC is this, that FSC and ASC into D minus D dash, or we will get this actual formula, that is mu2 equal to FSC ASC minus FCC into ASC into D minus D dash. So here FSC is a compressive stress in steel, AS is area of compression reinforcement, and minus this value we have to deduct. This thing we have already discussed that. So this is loss of concrete force, the force due to loss of concrete, that is FCC is the stress in concrete multiplied by a stress in concrete which is we lost due to the providing steel reinforcement in the compression zone, and ASC is the area of compression reinforcement. How much area of compression reinforcement we have provided? That's what concrete we have lost. So same thing we have to deduct from the total forces, total compressive force in due to the compression steel. So this will be like this, FSC ASC minus FCC ASC into D minus D dash. So neglecting area of loss of concrete, these we have to deduct because it is a small quantity compared to FSC. Then finally for our simplicity in calculation, we will take mu2 equal to FSC ASC into D minus D dash. So from that we required what is the area of compression steel is, that is ASC is equal to mu2, that is moment of resistance in section 2, by FSC is a stress in compression steel into D minus D dash. D is the effective depth of the beam section, D dash is the effective cover in compression zone. So now with this our calculation of AST and ASC over. But what actually we have to follow before calculating this AST and ASC, those detailed steps, almost we have 22 steps are there for designing a complete design of a doubly reinforced beams. Those are very easy steps. The maximum 90% of steps are similar to your design of singly reinforced beam. Just be concentrate on these steps. So let we'll discuss one by one steps. Right. So step 1 is, for given steel and D dash by D ratio, we have to determine FSC. It's a common step in your analysis part also. That is FSC. FSC means stress in compression steel. This can be calculated based on D dash by D ratio and given steel. So this table is given here. It is corresponding to the it is based on a table number F of your SP16. There I have copied this. There is grade of steel. This depend upon grade of steel and D dash by D ratio. And here we have a grade of steel vertical direction, D dash by D ratio in horizontal direction. So if you want to know what is FSC, that is compression stress in compression steel corresponding to the FE415 and D dash by D ratio 0.1. So here we'll take for Fe415 here, and d dash by d ratio is 0.1, that is 353 Newton per mm square. But sometime you may not get the exact value of this 0.05, 0.1, 0.15, 0.20 like ratios. Then we may get some intermediate values. For that also, that SP16 has given one provision that for intermediate values of d by d dash, sorry, d dash by d, it is a d dash by d, the next higher value may be used for finding FSC from the above table. Suppose if you get 0.9, d dash by d ratio is 0.9. What will be the next higher value? That is 0.1. So 0.09. D dash by d ratio is, if you get 0.09. What will be the next higher value? That is 0.1. So corresponding that value you consider as a calculating FSSC. So this is the first step. And second step, as usual, we have to calculate limiting depth of neutral axis. This limiting depth of neutral axis depends upon grade of steel, and these are the ready-made formula for calculating limiting depth of neutral axis. So as I told you, it depends upon the grade of steel. If the grade of steel is Fe250, then XU max can be calculated by using this formula, that is 0.53 D. Here D is the effective depth. Similarly for Fe415, that is 0.48 D, and for Fe500 it is 0.46 D. Like that we can calculate what is the depth of limiting depth of neutral axis is. Next, we have to calculate moment of resistance corresponding to the limiting depth of neutral axis, that is limiting moment of resistance. This can be calculated by using this formula, mu limit equal to 0.36 FCK B into XU max into D minus 0.42 XU max. This is the original formula. This formula can be modified like this by substituting various values of these. Here we have some factor, that is K, that is depend upon the grade of steel. So Fe415, that is 0.138 and 133 something for Fe500, like that. Like that you can use this formula or you can use this formula. You can calculate the moment of resistance corresponding to the maximum depth of neutral axis. Right. Next, now we have to calculate moment due to the applied factor loads. So you will give the factor load, or sometime directly will give the factor bending moment, that is given based on a given problem. But actually we have to calculate first what the dead load, live load, and based on that we have to calculate what is the design loads. From the design loads we have to calculate what are the design moments, or factored design moments, or factored moments I can say. Here, if your design is simply supported doubly reinforced beam, it is carrying a UDL, the uniformly distributed load of W, then the factored bending moment will be WL square by 8. If you are designing a cantilever beam with a doubly reinforcement and is subjected to a factored UDL, that is W, then the factored bending moment can be calculated by using this formula, WL square by 2. So from that we can calculate what is the applied bending moment. So this bending moment should be resisted by beam section, that is limiting moment of resistance. Generally, our limiting moment of resistance should be more or equal to this. Let us check. If it is more than that, what will happen? If mu is more than mu limit, what will happen? If mu is less than mu limit, what will happen? We will check in the next step. So this step is compare mu and mu limit. You know, mu is factored bending moment, mu limit is limiting moment of resistance. If your applied bending moment or factored bending moment is less than mu limit, then design that beam as a singly reinforced beam. There is no issue. If mu is greater than mu limit, your applied bending moment is greater than limiting moment of resistance, then we have to enhance our limiting moment of resistance by providing reinforcement in compression zone. So we are providing now the reinforcement in compression zone as well as tension zone. So we can call that beam as a doubly reinforced beam. So we have to design that beam as a doubly reinforced beams. Finally, if your applied bending moment is greater than limiting bending moment, then we have to design as a doubly reinforced beam. Right. Then how to design doubly reinforced beam? Then I have to calculate area of steel, area of tensile steel, and area of compression steel. So in step number 6, we have determined area of steel for a balanced section, that is AST1. Already we have derived the formula, that is AST1 can be calculated, that is mu limit by 0.87 Fy into D minus 0.42 XU max. What is mu limit? It is the moment of resistance of a singly reinforced beam, singly reinforced balanced beam. the moment of resistance of that particular beam, and Fy is the characteristic strength of a steel, and D is the effective depth of the beam. Xu max is the depth of neutral axis, limiting depth of neutral axis. So by knowing those values, we can calculate what is the AST1 is. You know how to calculate ME limit is, that is ME limit equal to K into FCK BD square. By using that formula, K values depends upon grade of steel. By knowing the grade of steel, we can calculate ME limit, and this Fy will provide you in the problem. D also will give the problem. Xu max we can calculate based on again grade of steel, that is based on Fe 250 how much, Fe 500, Fe 400 how much, Fe 500 how much. Those values present in your AS 456 2000 some tabular forms. From that you can take. Right. The step number 7 is determine the determination of a mu2 and AST2, that is, it is a moment of resistance or additional moment corresponding to section 2, right? Then area of steel provided, that is additional area of steel provided in tension zone. So those values we have to calculate now, that is mu2 equal to mu minus mu limit, that we can calculate. Mu limit is applied bending moment or factored bending moment. From that, if we deduct what is the limiting bending moment, then we can calculate what is the additional moment of resistance with respect to section 2, right? And already we have discussed in our beginning of this lecture how to calculate AST2 is, that AST2 corresponds to section 2, that is mu2 by 0.87 Fy into D minus D dash. You know what is Fy is? D is, you know, the effective depth of the beam. D dash is, it's the effective cover in compression zone. So after knowing the AST and AST2, we have to determine what is the total area of reinforcement provided in the tension zone. That is AST equal to AST1 plus AST2. So based on this AST obtained, choose suitable diameter of bar and provide them in the section. Right. Next one, step number 9, determination of a compression reinforcement, that is ASC. This also we have discussed, that ASC is equal to, that is a moment of resistance corresponding to the section 2 by FSC is that is stress in compression steel multiplied by D minus D dash. D is the effective depth of the beam, D dash is the effective cover in compression zone. By knowing all those values, and if you substitute those values in this formula, we will calculate what is the ASC is. Right. Now our design is over. Generally, design of doubly reinforced means calculation of ASC and AST. Because here dimension are restricted. Those the given dimension should be provided. With respect to the given dimension, we have to design our area of compression reinforcement and tension reinforcement. So next we go for some checks whether provided area of steel or provided dimensions are safe against the deflection, or they are safe within the limits of Codal provision or not. Those we have to check. Next, step number 10, we have to determine percentage of tensile reinforcement, that is called a PT. Then we have to calculate PT is equal to 100 AST by BD. Here 100 with respect to percentage, AST is total area of tensile reinforcement, B is the width of the beam, and small d is the effective depth of the beam. Then similarly calculate what is the percentage of compression reinforcement. That is again similar fashion we can calculate 100 ASC by BD. ASC is the area of compression steel by effective depth multiplied by your width of the beam. These two values will useful you for while we are checking against the deflection of a beam. Next, we have check for minimum area of reinforcement. So you know, as per class number 26.5.1.1 of A of IS 456 2000, the minimum area of tension reinforcement shall not be less than given by following. What is that? This AS is the minimum area of tension reinforcement. The area obtained should not be less than this value. That is AS by BD equal to 0.85 by Fi. This B value, D value and Fi value will present in your problem. According to that, we can calculate what is the minimum area of a tension reinforcement. So if you obtained AST, what are the area of total area of tension reinforcement should be greater than this area, that is minimum area of tension reinforcement. Otherwise, provide minimum reinforcement equal to AST as AS. So if you are getting the value AST is less than this AS, then how much value obtained for AS, that will be provided as a minimum area of reinforcement. Right. So here we have we have reinforcement in two zones, in tension zone and compression zone. But a code has given the minimum area of reinforcement provided in tension zone is with respect to this, but the code does not mention anything regarding this minimum area of compression reinforcement. So, but it has given for maximum area of reinforcement. Let us check what is a check for maximum area of reinforcement as well as compression in tension. Right. As per class number 26.5.1.1 of B of IS 456-2000, the maximum area of tension reinforcement should not exceed 0.04 BD. That means the maximum area of steel in tension what we obtained, that is AST, should not exceed 4% of gross cross-sectional area of a beam. That is, AST is less than 4% of BD. That 4% we can write it as a 0.04 B into D. And according to the class number 26.5.1.2 of IS 456-2000, they have given provision for maximum area of compression reinforcement also. That also shall not exceed 4% of BD. Similarly, how much the maximum limit for the tension reinforcement we have, same they have given for the compression reinforcement also. That is, ASC is less than 4% of gross cross-sectional area, that is 0.4 of BD. So finally, in your competitive exam, he may ask, what is the maximum area of compression reinforcement provided in doubly reinforced beam? What is the compression mean? That is 4% of total cross section. For tension means it is a 4% of gross cross section. What is the total reinforcement provided in doubly reinforcement? The total reinforcement means it combines your area of steel in tension, area of steel in compression. So altogether, if we take the total area of reinforcement should not be more than, that is 8% of gross cross-sectional area. That is, it is a 4%, it is a 4%, altogether it is a 8%. The questions may ask like that also. In a doubly reinforced beam, what is the area of reinforcement, total area of reinforcement should not be greater than 4% of BD, option A, 8% of BD, option B, 16% of BD, and so on. So answer is, most of the students will tick that 4% of BD. That is, 4% of BD is as an individual. If you take the compression, that is 4% of BD. If you take the compression, that is a 4% of BD. But in the question it was asked that is for total reinforcement should not exceed in a doubly reinforced beam is, that is 8% of BD. That is 8% of gross cross-sectional area or 0.08 of gross cross-sectional area. Just think when you are answering the question, just think twice. As given with respect to compression or tension or ask total, right? Okay. Next, check for deflection. It is class number 23.2.IS 456-2000. Here we have to consider, by checking a deflection, as we are providing reinforcement in compression as well as tension, we have to consider a percentage of tensile reinforcement as well as percentage of compression reinforcement. Let us take as a part A, by considering percentage of tension reinforcement and stress in steel under the service load Fs, the Fs can be calculated by using this formula. This formula will be available in your code also. So this graph I have copied from your IS 456-2000. There also he has mentioned that Fs equal to 0.58 Fi, area of cross section of steel required by area of cross sectional steel provided. It is in tension zone. So with respect to the Fs, I can calculate like this. So after calculating Fs, we have to calculate what is the modification factor. We can calculate a percentage of tensile reinforcement, we know. The Fs, based on that you can calculate what is the modification factor is. In this, if you observe this graph, on x-axis I have mentioned percentage of tensile reinforcement, on y-axis they are given modification factor, and there are some curves are there. Those curves are related to Fs, that is stress in steel under service load, and for particular value of percentage of steel and particular value of Fs, we can calculate the what is the modification factor on y-axis, right? And these are the basic values or I can say stiffness values for different type of beams. If it is cantilever beam, stiffness value depends upon L by D ratio. L by D is 7 for simply supported beam, 20, continuous beam 26. This value will helpful when you checking check for the deflection of a particular beam, right? Next, now in B category, consider percentage of compression reinforcement. Here also one graph is provided, the percentage of compression reinforcement on x-axis, a modification factor on y-axis. Based on the percentage of reinforcement, compression reinforcement and values, we can calculate what is the modification factor is. So this will be Kc, and Kc is the modification factor in compression zone, and Kt is the modification factor in tension with respect to tension steel. By obtaining these two value, we can calculate what is the L by D max is. L by D max means what maximum extent we can provide L by D ratio. So that is L by D max can be calculated is basic value multiplied by modification factor with respect to tension steel and modification factor with respect to the compression steel. These two value are calculated, and basic value we can obtain by this formula, this table. Yeah, if you are taking a simply supported beam, or if you are designing a simply supported doubly reinforced beam, then you can take that L by D ratio is 20, 20 multiplied by K value and Kc value, then you look at some ratio, that maximum ratio value should be greater than provided ratio of L by D. We can calculate what is the effective length and effective depth already given. From that we have to calculate what is the L by D ratio, L by D provided. That L by D provided must be less than L by D maximum. Then we can say it is safe against the deflection. So up to this steps, so up to step number 14, this is a design of doubly reinforced beam with respect to limit state of collapse in flexure. So in your board exam or university exam, he may ask you to design a doubly reinforced beam, a limit state of flexure only. If you mention like that, you have to design your problem up to this part only. That means checking off minimum area of tension reinforcement, maximum area of tension and compression reinforcement, and checking off check against the deflection. Up to this enough. Provided when they are given to design a doubly reinforced beam with respect to the limit state collapse of flexure, these 14 steps are enough. Now we are designing a complete design of a doubly reinforced beam. That's why I am proceeding to further steps. So that is design of shear reinforcement. So we have to provide, as we are providing main bars, distribution main bars in our beam, those main bars should be tied up with the shear reinforcement, and they should be hanged with a hanger bars. But here there is no provision of hanger bars. The compression reinforcement will act as a hanger bar. There, when you are providing a shear reinforcement in our singly reinforced beam, there is no reinforcement provided in the tension zone, but we have provided nominally some hanger bars to hold that main bar and stirrup in position. So for that, see a design of shear reinforcement for doubly reinforced beam. The similar steps what we have for our singly reinforced beam. First we have to determine the ultimate shear force. Anyhow we are designing shear reinforcement, we are resisting against the shear force. So for that we have to design how much amount of shear reinforcement required. For that, what is the amount of shear force is acting on that particular beam, that value we have to calculate. Again, the amount of shear reinforcement is depends upon type of loading condition, type of support condition, or I can say type of beam. Suppose if you are designing a cantilever beam with a uniformly distributed load, the maximum shear force occurs at the fixed support. That value will be Vu is equal to factored shear force equal Wu is a factored load multiplied by effective length. So this is how we can calculate the maximum shear force corresponding to the cantilever beam subjected to UDL. So if you are designing a simply supported doubly reinforced beam carrying a UDL throughout, the maximum shear force occurs at the support. That value will be say WL by 2. Right. Based on this, we can calculate what the factored shear force values. Then we have to calculate what is the nominal shear stress is. So for calculated nominal shear stress using the formula given in class number 40.1 of IS 456000, that is tau V equal to Vu by BD. You know, Vu we have calculated in previous step, and B is the width of the beam and small d is the effective depth. From that we can calculate what is the tau V nominal shear stress. Then we have to calculate maximum shear stress value of a concrete. This can be calculated based on a given grade of concrete. Why should we calculate whether the beam section is adequate to provision of a shear reinforcement or not? For checking purpose, we have to calculate that. So tau C max can be calculated according to table number 20 of IS 456 2000. It is depends upon the grade of concrete. So if you take M20 grade concrete, the tau C max is 2.8 like this, right? Then after obtaining the tau V and tau C max value, we have to compare these two. If you get your nominal shear stress is greater than the maximum shear stress of a concrete, then it is not adequate for providing shear reinforcement, because the maximum value is less than your nominal shear stress value. So then in this situation, we go for redesign at the member. That means we have to reduce the cross section of beam and reduce the area of steel something, and we go for we can make it less than our tau V is make it less than tau C max. If you are directly obtained your tau V is less than tau C max, then we go for further steps, right? Again, here we have to calculate one more term, that is calculate design shear strength. This can be found from the table number 19 of IS 456 2000. It will be obtained for area of tensile steel provided and the percentage of tensile steel and grade of concrete. So you may have doubt here. Here, sir, you have calculated percentage of compression and percentage of tension steel, but you are considering only area of a tension steel, percentage of a tension steel. Why? Generally, your shear cracks are obtained from the bottom of the beam. So for the bottom of the beam, which zone we have? Tension zone. So where we have to provide generally, and with respect to which steel we have to consider now? So in bottom of steel we have provided tension reinforcement. With respect to tension reinforcement only, we have to design our shear reinforcement. That is the reason why we have taken these values, the percentage of tension reinforcement and grade of concrete. So if you want to know what is the design shear strength of M20 grade concrete for a 0.5% of tensile reinforcement, say this is M20 and is a 0.5 percentage, the 0.48 is the 0.48 Newton for mm square is the design shear strength. Now we have to compare these two values. Say your tau V is greater than a tau C. What will happen? That means design shear strength is less than nominal shear stress. Then we have to go for design of the member. If your tau C is sufficient to resist, that means tau C is greater than tau V, then we can provide a nominal shear stress. So if in case if you are a minimum shear reinforcement consideration, what is the situation? Your tau C must be greater than tau V. Then we have to provide nominal shear reinforcement according to this class 26.5.1.6 of IS 456 2000, and based on this we can calculate minimum shear reinforcement in the form of stirrups, that is ASV by B into SVU, SV greater than or equal to 0.4 by 0.87 Fy. According to this formula we can calculate what is the area of that steel, right? And if that now case is different, so tau C is less than tau V, then we go for a design of shear. The shear reinforcement will be provided in, we have discussed three different forms, that is in the vertical stirrup or in the form of bent up bar along with vertical stirrup or inclined stirrup. Suppose for single bar of single group of parallel bars are bent up in the same cross section, then the shear resisting capacity of the bent up bar can be calculated by this formula, that is 0.87 Fy ASV sin alpha. Alpha is of 45 degrees. And this VUS is the strength of shear reinforcement, the shear resisting capacity of the shear reinforcement, I can say. Then see, as per class number 40 of C, the shear to be resisted by stirrups and bent up bar. So this is VUS equal to VU minus tau C BD. This how to calculate this VUS? Is that VU is the total shear to be resisted, and tau C BD is the shear resistance capacity of a particular concrete. In a beam section, total shear force should be resisted by concrete as well as steel. But we are designing a reinforcement, means what is the shear resisting capacity of a shear reinforcement provided? How much shear must be resisted by shear reinforcement provided? That means that in total shear force value, we have to deduct the shear resistance capacity of a concrete, the value obtained, which is VUS. With this VUS, we have to calculate the shear reinforcement. So this shear reinforcement can be divided like this. If you are providing a shear reinforcement in the form of bent up bars and stirrups, then 50% of value of this can be given to the bent up bars, and remaining 50% of this value we have to design stirrups. It may be inclined stirrup or it may be a vertical stirrup. Say, so if you are providing vertical stirrup, then you have to calculate what is the VUS. From this we can calculate spacing. VUS already known to you, that is 0.87 FY ASV by D into SU, and this VUS will be taken if you are providing bent up bars along with the vertical stirrup, that from the total shear resisting capacity of a shear reinforcement, in that we have to take only 50% value as this one. But if you are designing alone a vertical stirrup, then we can take total value whatever we obtained for the shear resisting capacity of shear reinforcement, that value you have to substitute here. From that we can calculate SV. After knowing this, from that you can, if you rearrange the time, SV will go here and VSU come here. From that you can calculate SVs. For inclined bars, you can calculate spacing like this, that 0.87 FY ASV D by VUS come here, will get here, SV value will be here, and alpha is the 45 degrees, that is the inclination of a stirrup. From that we can calculate what is spacing. Now how much spacing provided for provided calculated stirrups? The spacing of the stirrups shall be provided at least of following. One is spacing of stirrups to resist the total shear resisting capacity, total shear force. The spacing obtained from the minimum shear reinforcement, another condition. A maximum allowed spacing, that is 0.75 D or 300, whichever less. Among these three criteria, we have to take minimum value as a spacing for the stirrups. Next, we have a check for development length at a simply supported positive moments of reinforcement. If you are designing a doubly reinforced simply supported beam, there you have to check this. That is according to this class number 26 2.3.3 of IS 456-2000. That is LD is development length less than or equal to MI by VUV plus L0. MI is moment of resistance. It is corresponding to if steel provided is stressed up to the maximum level, that is 0.87 Fy. V is the shear force at the support, that is the factored shear force, and L0 is the anchorage length. This anchorage length will depend upon diameter of bar and angle of bend you have made. Anchorage length means, bending the bar or providing hooks at the end of the bar. Now that may be bent with some inclination. Here the length of the bar calculated like this as per IS 456-2000. For every angle, every bent of 45 degrees, then length of the anchorage bar should be 4 phi. 4 means that is a constant value. Phi is the diameter of bar, right? For if you are taking 90 degrees, that is 8 phi. If you take that 135 degrees, that is 12 phi. Like that we can calculate L0 values. And LD is the development length. The development length, you know, it is the minimum length of the bar which will be inserted into or embedded into the concrete so that it can resist the tensile force or whatever the force acting on the bar, which is making the bar to come out. To resist that from coming out of the bar, some stress will be developed. The stress will be transferred the force to the concrete in the form of a bond stress. Further to resist that bar, we have to insert some amount of length into the concrete, that is LD. That is LD should be greater than or equal to 0.87 Fi 5 by 4 tau BD. Tau BD is a bond stress. Fi is the characteristic strength of steel. Phi is the diameter of bar. We have to calculate like this. Tau BD is a bond stress, is given IS 456-2000. Based on this table, we can calculate what tau BD is. Bond stress in the limit state method of plain bars and tension shall be as given. That is for M20 grade. If you want to calculate, see, provided for limit state method, plain bar in tension, right? That is 1.2 is for M20 grade concrete. And if you are providing in the same tension zone a higher grade of steel, that is Fe415, that will be increased by 60%. Like that we can calculate and development length and substitute in the formula, we'll get what is the LD is. So this is all about today's lecture. Thank you.